It's a great pleasure to be here. I have no slides, so instead of showing the last slide, I'll just say happy birthday, Ludwig Bitich, and for your inspiration. So past, present, future, intertwiners. I'm not sure that I'll be always accurate attributing something to past or present, but I'll start from a very classical object, which goes back, as we'll see, to Gauss. This is just a linear recurrence, or you can think about it as linear difference equation. Vi equals AI1. This is not powers, this is just indices. Minus AI2 Vi minus 2 goes back to minus 1 to the power k Vi minus k minus 1. This is simple recurrence that allows you just you fix the first.
Algebraic.
It's a recurrence. You know first k terms, you recurrently compute the rest, or you can think about it as a difference equation. We already saw this equation in Misha Semyonov's talk in slightly without this stupid change of signs. I'll keep them for a moment because to avoid confusion with various signs. So recently, this very classical object with a special condition, namely, we consider difference equation with periodic coefficients, so Aij equals Ain. This is no. This is the point. This is the equation. The last and the first coefficients are fixed by 1. This is 1 or minus 1 to the power k. This is the specific of this equation. And we consider equations of this type having the following properties, that all solutions of these equations are periodic. Minus 1 to the power k, again, it's a kind of periodic.
What is the right side is in this relation for Aij equals
I plus n, sorry. So it's n periodic coefficients. The requirement is that all solutions of this equation are periodic. So if V satisfies to this equation, then Vi plus n equals minus 1 to the power k Vi.
But it's very rare because there is monotony.
It's not rare. It's codimension. If you consider all periodic operators, then codimension of E k plus 1 n is k plus 2. So depending on n, it depends on n k. So if n is big enough, it's pretty big, this space. So I will always assume that n is, that's why is bigger than k plus 2. And actually, through the rest of my talk, I'll also assume that k plus 1 and n are coprime. This is also essential. So this is a very classical object, which recently has attracted a lot of interest due to various studies current. It turns out it's on a crossroad on a theory of integrable systems. So the first motivation is, okay, it's again pentagram, but it's a different pentagon. It's not, it's a pentagon map. It's discrete integrable systems like pentagon map. So, or it's the same as a study of another objects. N-gons. This is the space of n-gons in C is the modular space of projectively equivalent n-gons in R or CPK. And actually, what is penta? Okay, Renat explained what is pentagram relation, what is pentagon map. So it's a classical statement from projective geometry. You take pentagon, you define a new pentagon just taking vertices of consecutive intersection of diagonals. So that was the original. This is the new pentagon. And it's known that this is projectively equivalent to the first one, just rotate and scale. But if you start with a sextagon, it will be different. But it turns out the dynamics, you iterate, you have a dynamics which is integrable in Liouville. So the transformation is on the space of n-gons, there is a canonical Poisson structure, and this is canonical map. And it, moreover, it can be integrated through algebraic geometrical methods, writing in theta function. So this is a first motivation. Another motivation is the theory of so-called Friese patterns. I don't know what's the right translation to the Russian. Friese. It's not freezed. Friese pattern. This is okay. I'll write it not in a traditional way because people. It was this notion was introduced by Coxeter and Conway, I believe in 60s, and this is you may think about it is as a strip of the width n W. On edges there are ones, so the distance between ones is W, and the requirement that okay you have add a certain number of zeros, so the requirement is that all minors, all k plus 1 times k plus 1 minors, just you move this pattern, have equal 1.
В середине какие-то цифры, да?
Okay, I'll prepare. This is the how it looks. W equal 2, k equals 1. So you just fill the first row. It's an arbitrary number. x2, x2, x1 is just parameter 2. And then you just start computing this. And you fill the whole line. And remarkably, it turns out that it becomes periodic.
This is Y system. Like a Y system.
This is Y system. Okay, again, the same equation is a...
You are saying Coxeter invented Y system in 60s.
He introduced Friese pattern for needs of representation theory. Don't ask me what problem he was solving, but...
All these things are...
Okay, as I said, everything is intertwined, so Sasha Volkov will talk more about this Y system.
So the statement is that if all the minors are ones, then it is this Y system we have there.
Yes, this is the simplest case. If all minors is 1, this is just... And it's if the width of this Friese pattern is 2, then it's 5 periodic. And this is...
Solid minus, not
As I said, solid minors. You just take a square k plus 2 and move it, and everywhere you get the matrix with determinant 1. So this is the notion of
So if you want to continue this picture beyond 0,
If I go to beyond zeros, it should be
-1.
1, and here it should, oh, -1. That's why I keep track of this sign. So it can be periodically extended through this thing. With these, okay, I'll come a little bit later. So we have space of differential equation, Friese patterns, and for me, the starting point of the work that I'm going to present now was an observation made by Tabachnikov, Ovsienko, Schwartz, and some French lady, I don't remember her name. A kind of duality. The Gale it's called combinatorial. Gale duality, which is the duality between the space of operators of differential equations of order k plus 1 with period n, and it's canonically isomorphic to n minus k minus 1 n. This is duality, which is generalization of classical Gale duality between n gons in respective projective space. There is well known, it's classical Gale duality for. Actually, this duality goes back to Gauss, who observed the following, and this is the example of such duality. So take the equation VI equals AI VI minus 1 minus V minus BI VI minus 2 plus VI minus 3. And suppose these are AI and BI are 5 periodic. And suppose all equations of this equation are 5 periodic. Then consider the equation of the second order, A VWI minus 1 minus WI minus 1, then all solutions automatically also, sorry, minus 2, yes. So if this equation has all solutions 5 periodic, then this equation is, all solutions of these equations are 5 antiperiodic. It was called Gauss miraculum, because it was a big surprise for me.
And that regardless of B.
Sorry?
That regardless of B.
Say it again.
No B, only A?
No, you see, it was a 3 order. You changed the order. It's order 3. So K here is 2, and K here is 1.
Is it true that V is a square of W, like this equation?
No. It's highly non-trivial.
It's like a darboon. It's like a
I'm going to explain it. Okay, so again, it's called Gauss miraculum, and it's also related to another observation by Gauss, which was very popular at the time. You consider just rational map from C2 to C2.
Which paper of Gauss is like?
I have a reference I'll give you in very old. So you are interested what is the impact factor of this journal? I don't know.
No. I mean, what subject? It's number theory or it's like some...
I think it's about, it's related to the following fact. This is Gauss map. You take a pair of numbers, A1, A2, and map it to another pair of numbers, which is A2. You just shift A2 and put here 1 plus A1 over A1, A2 minus 1. And iterate.
Gauss-Kuzmin map.
Yeah, and remarkably, it's going to be, you see, you iterate, you expect that rational combination will go more complex and so on. But remarkably, it's returned back in 5 steps. It's 5 periodic map. There is an even simpler map. And what is this map? You just consider this equation with periodic coefficients. So it's 5 period. The codimension is 3. So there are only 2 independent parameters. So it's A1, A2, it's A2, A3, and so on. So this is the reason. So if you just consider, for example, another map, A1, A2, goes to A2 plus 1 over, looks simpler, over A1. It's 10 periodic. So it's rational maps. So my goal is to try to explain this Gauss miracle. But first, I just want to correct this nonsense. Why these 2 coefficients should be the same. So the idea I'm going to explore is just to introduce in this difference equation a spectral parameter and see what we'll get. Just to develop a spectral Bloch-Flaquet spectral theory for difference operators, but of a special kind, which is not like we used to in case of Toda lattice or something. This is strictly triangle operators. So, okay, from now on, I'm going to erase this sign. So just making a gauge transform with diagonal matrix, which is -1 to the power I, we'll get the equation A. We get that this equation is equivalent to the, so if I denote psi I equals -1 to the power I di, then this equation becomes a spectral equation for difference operator L, which is of the order Tn plus 1. T is a shift k plus 1 plus AI 1 Tk plus blah 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 plus, and that is essential, plus AI k T, and there is no free term. So if you write it as a matrix, there is zeros on the diagonal. There is ones on the diagonal shifted by k plus 1. The rest is filled by coefficient. This is the equation. And also periodic coefficient. So this...
Why there is index I?
Sorry?
There is index I, so there is Li there.
You see, when you write differential equation d over dx squared plus u of x, you don't ask what is x, is it an index or not? You just write L. So it's the same. So it's a space. Oh. Then, okay, if you confuse, then I'll write L psi I equals T applied to psi. Psi is the... Okay. Why you don't ask about this? Okay, so I is a row, J is a column, and so my first goal is Flaquet spectral theory for this operator. It brings a lot of... So again, I don't want to look at this equation. I want to find the explanation just deforming it first, making it as a part of the family, because this is equation coincides with E equals -1. So if you put at one particular value of energy, you get the equation we start with. And at the moment, I'll forget about the condition that all solutions are periodic. Just the spectral theory of periodic operator, strictly triangle operator. It's so I erase this T. So the first observation or the result I would like to state is the following. Okay, spectral curve. As usual, when you start with a differential or difference operator of Fouquet spectral theory, you are looking on block solutions. Block solutions which are solutions to this equation and which are eigenfunctions also for monodromy operator. And as usual, you get algebraic relation between eigenvalues of two commuting operators. They commute because the coefficients are periodic.
N is the same as K?
So, no. You have two parameters. You have order of differential operator and you have a period of coefficients. So, you can think about dk plus 1 n is a space of operators L I erased with periodic coefficients k I plus n j equals a I j. So this is the setting. The total dimension of this space is of course k n. This is the space of coefficients. Okay. So the statement, spectral curve, you define it in the usual way. You just take the determinant. So which one? You take space of functions which satisfies this relation. So instead of writing this infinite upper triangular matrix, so as usual you have zeros on the diagonal, you have here coefficients, here ones, and when you move outside of your square, you put here the same, multiplying them by w. And then you compute the determinant of such matrix, L E minus L of W. This is equal 0. But there is a very strange first looking condition. So you will get algebraic relation RWE equals, and it has the form, this RWE has the structure WK plus 1 minus e to the power n plus some alpha Rij W to the power I e to the power j, and here summation goes for I bigger than 0 and such that I times n plus j times k plus 1 less than k n k plus 1. So in other words, this is the polynomial whose Newton polygon looks the following. This is triangles with vertices n 0, k plus 1, 0, and you just cut away a piece. So it doesn't contain this term. It contains only vertex 1, 0. So this is the triangle with such vertices. It's now just let me elaborate on specifics of such curves defined by this equation, because it would be crucial. Oh, I have to hurry. I have to hurry. Okay, so it turns out that this equation defines you some algebraic affine curve in C2, so in space of WE, you have algebraic relation. You have to compactify. So at infinity, there is one point at which, so gamma is this algebraic curve defined by this equation is compactified by one point at which all sheets come together. This is typical. What is unusual is that because of this simple form, so R0E is just e to the power n. There are no lower terms. It turns out that, for example, the point W equals 0 and e equals 0 is obviously on this curve. The remarkable thing that over e equals 0 there are k plus 1 sheets. One sheet is, because of this property, is singled out by the property that at this point W has 0 of order. So here it has a pole of order n. At this point W has 0 of order n. So we have a curve with 2 points. This is a typical situation for 2D Toda lattice, 2D Toda equation. And the statement is that, I'll show you the example. So the theorem is that the space of all operators, so this is just linear space of dimension which I erase of dimension kn, is fibered over the space of such curves with a fiber which is Jacobian. So it's a typical structure. So of all of this space D k plus 1 n has a structure of a fiber of a completely integrable system. So space of curves here is Jacobians. And moreover, it turns out that eigenfunctions for this spectral theory is just a classical discrete Baker-Heisser function. So we'll come precisely to the setting of completely integrable systems. Let me just show you an example which worth to mention. The simplest case when we're dealing with coefficient with equation L is t squared plus a1 AIT. So this is the equation psi I plus 2 plus AI psi I plus 1 plus equals E psi I. So it's like in Toda lattice. But the spectral parameter, first of all, we never see in Toda lattice fixed coefficients here. And now the spectral parameter not in the middle. And it makes the whole theory much more interesting. And let me just show you how looks the spectral curves. It's again, in this case, for such operators, the spectral curve is hyperelliptic. So it's W squared. The period should be odd because of co-prime condition, I assume from the beginning. And it has the form, it's polynomial of order m plus minus e to the power 2m plus 1 equals 0. So, and what are these operators? Just any sequence, periodic sequence of numbers, a 2m plus 1. And so any sequence of the space of dimension 2m plus 1 can be represented as a fibration of the space of such hyperelliptic curves. Again, we used to think about hyperelliptic curves in context of Toda lattice with 2 marked points, but usually these 2 marked points at infinity. So at infinity here we have 1 marked point. The second one comes as on one of the sheets on the previous one. Okay, so far this is the spectral theory of general periodic operators, strictly triangle periodic operators. Now, so if you look on the family of spectral curves defined by this equation, the number of parameters, namely the number of points in this triangle, is so the number of Rij is k n plus 1 over 2. Genus of the corresponding curve is k n minus 1 over 2. So if you look, sum up this dimension, we'll get precisely the total dimension. So of course it's a genus of a smooth curve. Now I'll come to the point looking on special solution. On special, okay, I call this, because it's too lengthy to say all the time, it's a differential equation whose all solutions are periodic. Let's call them superperiodic. I don't know it's, in what sense it's super, but so far in this area it was not, this notion is not occupied. So the spectral curve corresponding to periodic, to these superperiodic operators is never smooth by definition, because so spectral curve corresponding to L in this special class of difference equation is always singular over E equals 0 equals 1. All solutions have to be with the same multiplicator. So the structure of this curve should look like intersection at one point, all sheets. So it's always singular. So gamma spectral is always singular. So we can consider its normalization. Usually when you have a singular spectral curve, Bloch functions are not as nicely defined. You have to put some gluing condition. Sometimes it's a mess. Remarkably, the requirement that all solutions of this equation should be they're linear independent implies that if you take the Bloch function on the spectral curve and lift it on the normalization, the curve that you just move away all this intersection point, becomes again the Baker-Hazer function. The number of poles of this function drops down because all extra poles come to this point and annihilate. And so you have again a typical setting when you have a smooth curve with two marked points. Now I would like, yes?
Can you calculate the period matrix?
Of this curve?
Yes.
Of course not. It's one, okay, our parameters are curves. Of course, I cannot compute, but there are now programs. You just plug in this equation, they will give you a basis of cycles and periods. Of course, it's no, no. So the answer is simple. No, I cannot. I cannot. But again. I have 10 minutes?
5 minutes.
5 minutes. Okay, So, what are properties of such a curve that comes as a normalization of this spectral curve? Let me just avoid this. It becomes too technical. I'll state what I'm going to formulate in a very simple terms. Let's just return back to our original setting. In differential equation, in the original calculus of ordinary differential equation, we always know that if you have differential equation, or differential operator whose kernel contains the kernel of another differential operator, then one is divisible by the other. So let's look on the original property of this equation. So if all solutions of the equation L plus 1, I recall E equals -1, L plus 1 are all periodic, that means that the kernel of this operator contains the kernel of operator -1 to the power n plus k. It's not pure periodic. It should be taken into account, this order. So what does that mean? That means that, or you can take the definition of this special operator. So the kernel of this operator is contained in the kernel of this operator. That means that it is divisible, n plus -1 over n plus k. There exists another operator, let's call it left plus -1 over n plus k. So this is the condition that all solutions of this operator are periodic. Periodic, antiperiodic. But if it's divisible from right, it's divisible from left. So there exists another operator, L right plus -1 over n plus k. This is the definition. So we consider operators such that this operator is divisible by this one. Okay. So theorem, which surprisingly, I cannot prove without going through this whole machinery, that right and left divisor are equal to each other. It should be possible directly to check. I don't know. From pure algebraic structure, I don't know how to derive. You have to go through the theory of spectral theory to prove this. And actually, it turns out that, and that implies, so let's call this divisor L. Then that implies that L commutes with L. So every operator, special superperiodic operator, there exists an operator, so it has order k plus 1. This has order n minus k minus 1. And this is the Gale duality. This second commuting operator, it's almost Gale dual. I have to state more precisely this statement. More precisely, on the space d k plus 1 n, there is an involution going to the space of operators of order n minus k, to the same space, k plus 1 n for all k. And it's the following. So L sigma by definition, so what we do, we just, first we take formal conjugate, so we transpose plus 1, shift by t, k plus t minus k minus 1. and subtract 1. So this is the involution. So the claim is that this operator L is so Gale dual in the notion of Tabachnikov, Ovsienko, and others is nothing but you take commuting operator, you apply this involution, and you conjugate with matrices, diagonal matrices with 1 and -1 on the diagonal. So it comes that any operator which is special, there exists a commuting operator. So is it characteristic? It turns out yes. The operator is special if and only if they, I have to be more careful, if and only if there exists a commuting operator. Let me just state it more precisely. Okay. Now I'll put the condition that k plus 1, 2k plus 1 is less than n. It's duality, so I'll choose which one, less than half of n. So if, so theorem, let L be just periodic difference operator of order k plus 1, and suppose there exists another operator k, suppose do I have a red card? Suppose there exists an operator k in d k plus in d n minus k minus 1 n, which commutes L commuting with k. Then this operator L is superperiodic. It's almost superperiodic. So it's superperiodic is superperiodic up to simple transformation. So TC is the following transformation. If you have operator and constant C, you form diagonal matrix. C is diagonal matrix with Ci on the diagonal. It's like rescaling. So just conjugate, and to make this operator monic, namely to keep this coefficient fixed, you have to multiply it by C to the power k plus 1. So up to this, so this transformation, what does? It moves E equals -1 to any other value. So this is the class of operator you obtain by this transformation. It's a class of operator for which, for some C, for some E, all solutions would be periodic or antiperiodic. So just it's simple scaling. So up to this transformation, the existence of commuting operator is necessarily sufficient for operator to be super periodic. Okay. What's the future? I don't know.
What about Gauss problem? Can you say solution to the Gauss question?
To this mirifical?
Yeah.
Okay, I gave these two operators. If you choose, it's exactly this. I don't know what is. It would be. It's strange. In all this theory of these free wise systems, all formulas usually are determinant formulas. Now, this way gives you another possibility to parameterize, express everything in terms of theta functions, which might be useful, might be not. I don't know. But
Maybe maybe I don't understand something, but it seems to me that you use your index I as space,
Yes. Yes.
but
And
you can do it as time also. And then, well, because of your periodic systems, there are certainly, now you have time, isn't it?
no, it's really space.
If so, then of course you can introduce periodic structure and see evolution.
As you see, it would be again. Oh, thanks for asking, because might be it's an answer what would be the future. Okay, there is a machinery which tells you whenever you have a difference, a linear operator with a spectral parameter, you may introduce. There is a canonical way to write a symplectic structure. It would be extremely interesting now to compare it with what Misha did. And because it's, you see, we used to think about what is the kind of solutions for
Symplectic structure for such doesn't depend on energy. It's just for fixed energy, you can say.
yes, of course, but I don't know. It's just a simple.
But still periodicity in time, because it is.
No, I prefer to. It's periodicity in time.
Symplectic structure only two
Just one
initial
question.
data A1 and A2, and then you somehow move as you
Problem, yeah.
explicitly.
Yes.
In your approach, you just insisted that it's just strictly periodic, but just a more generic situation is that you have monodromy. And what will remain of your duality if you look for generic?
There is no duality in the generic case. Yes. Surprisingly not. Because you see, the specific of this problem is the following. Because if you take generic operator, then there are only, on the spectral curve, there is only two, the ring of functions on this curve are generated by two, W and E. The specific and the duality is the following. When you have as the singular curve, there is another function which is nothing but W minus 1 divided by or E plus 1. It's called K. Because all zeros of this operator it's like divisibility I show. So the presence of this extra function, so the generator now not E and W, which is the smallest in the general case. There is another function with degree exactly n minus k minus 1. And this is only for this case. So the genus drops, they appear in new functions, new commuting operators. So it's precisely the setting for these superperiodic operators.
From the point of view of this generic Poisson structure which I described, this is of course a Poisson manifold, but it's very special.
Yeah, so it will be interesting to consider the restriction of what kind of symplectic structure on this submanifold will be induced. I don't know.
If no questions, let's thank the speaker again.